Okay, one of the absolutely most important theorems in geometry is this one here, that is called the Pythagorean Theorem. And trust me when I tell you that it is used like no other, and has really, served mankind well. So what it says is that the square of the measure of one leg plus the square of the measure of another leg is equal to and the sum of the squares of those two measures is equal to the square of the hypotenuse. So in this triangle ABC, we would say leg AC, the measure of leg AC, which I have marked here S, squared. See this little arrow like this? This is typical that you'll see in programming on the computer. It's not easy to write superscript, a little tiny 2 up there. So that little thing, which sometimes is called the caret, and it's found on your keyboard, it's Shift 6. That indicates that this part over here should be in the superscript. There should be a little 2 up here that says AC squared. So that's just what we're doing here. Leg squared plus leg squared equals hypotenuse squared. So in this triangle ABC that we have here, it's a right triangle. Okay, on this side here, AC, which I've also got marked as S. So that measure of AC squared plus the measure of BC squared, which I have marked R, that's that measure there, is equal to the measure of AB squared, which is the hypotenuse, and I have that measured as T. That length from A to B is measured as T. So that's all we're thinking about right now. So now, in order to prove this, we're going to use the properties of similarity and write some proportions. Okay, so let's start. Let's start by seeing how we set this up. And the key for you to be, because you have to write this too, you're going to have to go through this whole thing. So make sure that you do a good job with your diagrams. Maybe you can even do a better job than I have here. But I started in GeoGebra making a right triangle. Then I made a perpendicular that went through the opposite vertex. And I took a picture of it. And I made I made these triangles here, and I made rigid copies of it. And maybe I'll just show you that real quick, that process real quick here. So, I start by making my right triangle, which means I start with a segment, right? Then I add in a perpendicular that goes through one of the endpoints, and then I put a point on the segment, which is point C. And then I can connect them using the polygon tool and make my right triangle. And then I made my line disappear. All I did was, click that button right there. It makes the line go away so you can't see it. It's still there, but you can't see it. And then I made my perpendicular. So I used my perpendicular tool. Perpendicular line goes through point A. And then I used my intersection tool. That's the new point where it intersects. And I placed intersection point there. And then I made a segment. I actually drew a segment using my segment tool here. I drew a segment between A and D, and then I could make the line go away, and then I could see that right there. So I drew these triangles out using the polygon tool one at a time, and then I used this rigid polygon tool, okay? And I slid this up out of the way. You'll see I made a copy of this triangle, then I made a copy of the other triangle using the rigid, and I just separated them so I could see them. So now I have my original triangle here. And what would even been better is to get rid of this segment right there. That's segment E. We don't need to see it, all right? And we can see it there, that's fine. Wherever else we had that same segment. Do I need to get, no, I need it there too. But it may exist somewhere else here. How about that one? Yeah. And anywhere else that I've got it, how about there? There you go. And in fact, now point D can go off. So now I've got that's a better diagram for you. You should draw this diagram right here, okay? Anyway, we'll go back to, my diagram here. And let's work through the logic. So we're gonna, what we say, let a perpendicular go through side AB, such that it is perpendicular and goes through the opposite vertex or vertex C, thus creating two new triangles, triangle AXC and triangle CXB. Okay, these two triangles, AXC and CXB. to go along with our original triangle ACB. Okay, now, so now we have 3 triangles. There's my big one, and what I've done is I've marked each of the points. So there's point X, A, C, and B. C and B are represented over here. And then, because I'm not going to want to call this BC every time, and the letters kind of get confusing, I just said let this measure be called R, however many R units that is. And this whole thing here was T, right? This whole measure here is T. This measure here was S, right? Oh, sorry. And this measure, this diagonal, is U. So, and then I said take T and divide it up and call this side V units and that side W units. So they're just the parts of T, okay? Because this would be V units here and this would be W units there. Okay, so now I have my diagram. So let's go through it. First thing we're going to do is we're going to prove that these triangles are all similar. They have to be similar or we can't do anything about it. So how are we going to prove it? Well, we start by saying, hey, this angle right here, BXC, right, follow along up here and you'll see BXC is congruent to ACB. Why? Because this is a right angle and that was a right angle. Remember, we said let a line be perpendicular, so this has to be a right angle. So all right angles are congruent, okay? And then angle B here is congruent to angle B. So we have this angle and B, and this angle and B are congruent. Therefore, by angle-angle similarity, these 2 triangles are congruent. Now, I just wrote here, by the same logic, these 2 triangles also have to be congruent. And what we would say is, here's our right angle right here, right? And it has to be congruent to ACB, our right angle here, because they're both right angles. And here is angle A has to be congruent to angle A, and that's by what we call the reflexive property, right? That it's congruent to itself. Don't forget the reflexive property. So using the same logic, we've now proven that this is also similar to this triangle. Therefore, they're all 3 similar to each other. They're all 3 similar to each other. All right, now, what does that mean? Well, if we use the properties of similarity, okay, this particular property says, one of the properties of similarity says that corresponding sides are similar. And therefore, we can write, I'm sorry, that shouldn't say similar, that should say that corresponding sides are proportional. Let me see if I can get in here and just change that real quick. That word should be, they are proportional, meaning we can write ratios out of them and the proportion will stay true. So now let's take a look at what I'm dealing with. I'm going to start with CXB and ACB right here. So I say if I take the hypotenuse of CXB, right, that's R, I can put it over the hypotenuse of ACB, which is measure T. So R can go over T in a ratio, in a proportion that's going to be equal to, let me pick 2 other sides. I'll take the long side of CXB, which is measured at W, and the long side of ACB, which is measured at R. So in the way that we put hypotenuse over hypotenuse, R over T, we can put long side over long side, W over R. So we end up with R over T equals W over R. That's this part right here. So now if we know that R over T equals W over R, we multiply both sides by these denominators to make them go away. So we're going to multiply both sides by T and both sides by R. We multiply both sides by T, the T's are going to cancel. And that's the multiplication property says we can do that. T's cancel, we end up over here with just R squared. So there's my R squared, right? On the right side, the R's are going to cancel, and we're going to end up with just TW, or WT. So after we simplify, we end up with R squared equals WT. Okay, and that all we did was we wrote some equivalent ratios because we know that these sides are proportional. Okay, now we come over here to this triangle here and the other triangle. So we're looking at AXC and ACB. So let's take the hypotenuse of AXC, which is S, and put it over the hypotenuse of ACB, which is T. So we have S over T. And we know that that's going to be equal to, we take here the short side, which is this measure right here, V, over the short side here, which is S. So we end up with S over T, hypotenuse over hypotenuse, is equal to V over S, short side over short side. And so ST over T equals V over S, all right? And we're going to use the same concept here that we did above. We're going to multiply by the denominators, get the denominators to go away. So we're multiplying by T and we're multiplying by S on both sides. So TS on this side, the T's are going to cancel. We're going to end up with S squared on the left. Multiply TS on this side, the S's are going to cancel. We're going to end up with VT on the right, or TV. So I have S squared equals TV. So now, let's say we add this value R squared to both sides. We can just add that. That is the addition property of equality, says we can add the same thing. So R squared plus S squared equals TV plus R squared. And we added R squared to both sides, right? And because R squared is equal to WT, that's what we proved up here, we're going to substitute, and instead of calling this R squared, we're going to say R squared plus S squared is equal to TV plus WT. So now we do a little trick that we see in mathematics. If we see T times V plus W times T, we have a T in both the beginning, in both terms here, we can extract the T, right? This is called factoring. We're extracting the T's. We're taking the T out of the V, TV, and we're taking the T out of the WT. We're pulling it out over here and we're writing T times, and then what's left behind? These are two factors here. The factor inside is a binomial, V plus W, two terms right here. So T times V plus W. Well, that's good. But let's see what V plus W was. V was this length, right? And W was this length. So what happened when we added V and W together? V and W together measures how much? By the segment addition property, if we add V and W together, we get right back to T, right? That's what T was. That's how we defined it. So now if we have T times V plus W, we can substitute and we get T times T, right? And then that becomes T squared. So this is really the proof. Look what we have. I have R squared, which is this leg squared, plus S squared, which is this leg squared, is equal to T squared, which is my hypotenuse squared. I have proven that because I can make these similar triangles and that I know the sides, the corresponding sides are proportional, that I can write equivalent ratios that set them up, and using a little algebra to simplify and move things around, I can end up with Pythagorean Theorem. So go ahead and construct your thing here and make sure you understand it well, and you're going to want to make a move note where you talk through this a little bit, and you might want to practice it a time or two before you're done.